it's really fascinating to see so many old faces we haven't seen for 20 years, sometimes 30 years, but it's really wonderful. Now, you know, I started out in Berkeley not doing earthquake engineering. I had no interest in earthquake engineering. I was only interested in mechanics. But in 1971, I was due for a sabbatical leave. And I decided to take sabbatical leave in New Zealand because I was invited by the New Zealand Government Department of Scientific and Industrial Research to go to New Zealand. But they assigned me to a group called the Engineering Seismology Section. Earthquake engineering. Why? Well, I didn't know, but I got to New Zealand and I found that they had a fascinating problem that I could do something about. What they had done was this, very interesting problem. The Ministry of Works, which built the railroads in New Zealand at this time, had a big problem. They were trying to design a very tall railway viaduct structure, the piers. The piers were 200 meters tall, and they were reinforced concrete. Now, you get a very tall structure with a very heavy load on top, the railroad train, freight train. And when they did the seismic analysis of it, nothing worked. Couldn't do it because as an earthquake forced the thing to go back and forth, the tension in the reinforced concrete leg just blew apart. Couldn't take the tension. So they had this interesting idea. They decided they'd let the leg step up. But, you know, structural engineers don't like the building to jump off the foundation, you know. But that was the only solution they had. And now, at that point, I joined the section. And they knew, and I knew, that the only way you could make this work was to have some energy dissipating, energy absorbing device in the system. My background in mechanics led me to suggest that steel yielding would be a great way to absorb this energy. And I told them, I said, torsion bars are very stable and you can twist them back and forth into the plastic range many, many cycles. So they agreed and we tried it. And they had test equipment out there, but nothing dynamic, just static testing. And I first suggested, let's take a circular torsion bar and check it. Well, no good, because you couldn't grip it. So we went to a square bar. Better, you could grip it, but eventually, and you know, I was there for a year, and as the year progressed, we tested so many different yielding elements that we finally settled on a rectangular bar. And there was all kinds of other details. There's samples of them in the lab here. But it worked. We demonstrated this to the Ministry of Works, and they accepted it. And these rectangular torsion bars, they're huge actually, the real ones that go into the bridge, but they're in the bridge. They were installed in the feet of the bridge. And really, it's a simple idea, but it's a terrific idea because the torsion bar yielding is symmetric. It doesn't matter whether you twist it that way or twist it that way. So when the foot's lifting up, the torsion bar absorbs the energy. When the foot stops going up and starts to come down again, it absorbs more energy. And the whole system worked. We demonstrated it, and they accepted it. And these rectangular torsion bars were installed in the feet of this stepping bridge. And they're still there. 71, so that's a long time ago. They're still there, and there hasn't been an earthquake in that since, so they must have worked. So I came back to Berkeley in 1972, all excited about earthquake engineering, which I never was before. And amazing thing, first thing I found out, we had a shake table. I didn't know anything about it before I went, and there was when I got back. Also, they had a model. It was just a 3-story frame, maybe total a couple of tons at most. I don't really remember now. But it was a model, it had a shake table, and more than that, they had money. And I said, I want to simulate the stepping bridge with the three-story model and test it on a shake table. Approved right away, 1972. And I designed the scale models of the yielding devices, stuck them on the feet. It was only 4 feet, just two by two. And so we've got the things in there, tested on the shake table, starting, of course, in those days, very low input, and then gradually beefing it up until it was pretty big input, and it worked. And published it, the first EERC report. It was really quite impressive. And then, fired up with enthusiasm for steel-yielding devices, because we had tried in New Zealand torsion bars, bending bars, all sorts of things before we settled on the torsion bar. So sitting out here, we kept thinking, what can we do to incorporate these into real structures? And the big problem is to get a yielding device to act as an energy absorber, you got to have a lot of displacement. How can you get displacement? Structural engineers really don't like to have stepping buildings, so that's not an option. But just by sheer good fortune, I had been approached by some people in the United Kingdom, an English research group there, called the Malaysian Rubber Producers Research Association. And they thought that it might be possible to use bridge bearings, which they had developed there, natural rubber bridge bearings, and with that make a bearing the building could have, and it would have a lot of displacement. So, fantastic. First thing we did was get them to make us some handmade natural rubber isolators, which were small, and put them under the frame. We may have pictures. Ian probably has some pictures that we'll show you in the next talk of this actual handmade model. Shook it. It was amazing. The reduction of acceleration inside the structure compared with the acceleration input by the shake table was fantastic, about a factor of 10. And that was just with the plain rubber, no energy device. So then we stuck torsion bar, bending bar, We even went as far as looking into the possibility of using viscoelastic devices as energy absorbers, which meant we went down to Grand Auto and got some car shocks, and we incorporated them in there. 1972, and tried it. Everything worked okay. It's good. But the people at Malaysian Rubber come up with an even better scheme. I mean, we wrote all these. There was EERC reports for the yielding and the other stuff. They incorporated the damping, the energy absorption, into the rubber compound itself. And after a lot of experiments on the shake table, a lot of calculations, a lot of theoretical analysis, we ended up with what we described as the high damping rubber isolation system. Good name. HDR, high damping rubber. And this approach was used not too long after in the first isolated building in the United States, which was a large, you usually think you start with a small building and then get bigger. No, we started at the top, and I designed bearings for this full-size building, a legal services center in Rancho Cucamonga in Southern California. And the bearings were big, 30 inches in diameter outside. That was big bearings. But there was no way to test them. But what? We built a testing frame out in the lab, in the shake table building, in space there, that was able to test these bearings, 30-inch diameter, and we tested, estimated maximum possible displacement, 8 inches. We tested them to 15 inches out in the lab here, and they were installed in the building, and it was built in early 1980, finished open to the public in 1983, and it's been through several earthquakes since then, worked perfectly. And that was a high damping rubber. It's now used widely, all worldwide, that particular thing. But before I leave my train of thought here, getting back to the shake table, we had various other ideas about isolation systems. And we did a lot of different tests. One of the things that came up was that the DuPont company, we published so many things, and they read the thing, and they said, DuPont makes artificial rubber, so-called neoprene. So they said, would you like to test the neoprene bearings that we could provide for you? And they did. They provided us an enormous number of bearings made of neoprene. Small, that's okay. And we installed them and tested them. And they worked pretty well. Not super, but okay. But the thing is that we did this, I think, in the early 1980s, the neoprene tests. Maybe before, maybe in the late 1970s. But a few years ago, Tracy Becker came to me in my office, and she said, we have scheduled 2 weeks on the shake table, but we don't need it. We've got a week free. Have you anything we can do? And I said, of course. I said, I have 6 6 neoprene bearings in my office that have been there for 30 years. And I said, how many feet does your model have? And she said 6. I said, I got 6 bearings here. And we installed them under her frame and retested them 30 years later after the tests that we had done. Now, by this time, of course, the controllers were better, but we were able to reproduce exactly the same tests we did in the 79-80 period with these bearings which had never been tested. They were in my office in the original wrappers. And we were able to test them and compare. And, this is valuable information because, buildings are in the bearings are in the building for nominally 50 years. Does it change? It's important to know. And this was very good data published. And it actually was of great interest to French earthquake engineering because all the French nuclear reactors are built on neoprene bearings. And they're supposed to last for 50 years or more. So it's an interest. They were interested in how the rubber changed over the years. In fact, I'll tell you what it was. The rubber got stiffer and the damping got lower. But it wasn't really too bad. I'd say that the stiffness of the bearing maybe was 20% more than the original. But that only affects the period by square root. So it really doesn't change the period by maybe 10%. But that's trivial because the over-design of nuclear power plants is enormous, as you all know. Well, just to go back to my original discussion about the isolation bearings. We first tested with a 3-story frame. Then we had a 4-story frame with 8 feet. And then we had a 5-story frame with 8 feet. Same frame, really. And then we had a 9-story frame by clamping the 2 frames together, locking them together. And it went right up to the top. We didn't need a hole in the ceiling then, but it got right to the top. And then we did testing there with rubber bearings, Malaysian rubber bearings, and we found that the 9-story frame, 4 stories fine, 5 stories fine, 9-story frame, you get uplift on the bearings. And rubber, natural rubber, neoprene rubber, doesn't like tension. So we had to design the cutest little gadget. All these bearings were hollow. We designed a really cute little gadget that sat inside the bearing itself, and so the tension on the rubber was transferred to this gadget. It didn't affect the normal movement of the bearing at all, but when it got to a certain point, it took the tension and everything. But we also found a side issue which we had not anticipated. When I say we, I mean me. I had not anticipated that it would affect the displacement. Now, you need to get a limit. Most isolated buildings nowadays are built with a moat around the side, and the stopping of the building is impact against the moat. I always thought that was a terrible idea. But this gadget that we had designed had that advantage that you could move it back and forth. At a certain point, if you moved it too far, it then activated the vertical stiffness of the bearings, which is about 40 times the horizontal stiffness. And the system stiffened up. And it stopped the movement gently, not sudden impact. A much better design. That, in fact, a building using that technique was built in Southern California, in the east of Los Angeles. It was the Los Angeles County Fire Control Center. And it was built again in the middle 80s using this concept. It's still there. It's been through lots of earthquakes, more than the other one, and it's functioned perfectly well since then. It has not been replicated anywhere else in the world, which is unfortunate because it's the simplest way to deal with this problem. However, we have done so many different tests out the field station on the shake table over the years. We're not just isolation or energy dissipation. We also did piping systems. We did shaking of steam generators in nuclear plants. All of this funded by the Electric Power Research Institute down in the San Jose area. They funded a whole lot of stuff for us. Some funding for the isolation work came from Malaysian rubber, not much. Most of it came from the National Science Foundation. They got very keen on the idea for a few years, and we were very well supported here. There'll be more about other tests in the past. The last test I did was the one I did with Tracy's frame and the old bearings. And that was probably, it would be 2012, something like that. And that was the last. But just forgetting about our isolation work and so on, we also did a lot of testing on other stuff, energy absorbing stuff, particularly with shape memory alloys. We did a lot of that work too. Not so much on the shake table, but a small testing. But the other thing I'd like to say just before, I don't want to get the impression that I was the only person using the shake table all the years. I was many, many people. Bertaro was using it for lots of stuff. And the frames, the 3-story frame, the 4-story, 5-story, 9-story, we didn't build those. They were there. The other people were using them for other purposes. So the shake table has been really a huge generator of data and reports. In the very first years of testing out here, the students that helped me were master's degree students, because in the 70s, master's students had to write a thesis, and eventually the faculty couldn't take it anymore. So the master's students did the bulk of the work. John Eidinger, who I know is here, he was one of my master's students. Dan Chitty, there were a few. But then after a certain point, when they didn't have to do their master's thesis anymore, it became PhD students that did the work, and some others. I would say we generated an enormous number of published papers and EERC reports from the 1980 onwards. But besides what I did myself, I think the importance of the shake table was this. Before the shake table, the structural engineering profession seemed to believe that earthquake engineering was static, that all you needed to do was apply a side load to the building, design it for that. And the problem with that is, if you want to make the building more stronger, more secure, you have to add a lot of reinforcement to the building, which is expensive. Whereas after the shake table, the profession saw the process is dynamic. And once you accept that earthquake engineering is a dynamic process, then modification of the dynamics becomes essential. And it provides solutions that are better, more logical, and cheaper. And that led to the use of energy dissipating systems, isolation systems, and other mechanisms for absorbing dynamic energy. And that, I think, is the true benefit that the shake table has brought to the structural engineering profession. Okay, it's enough from me.